Good morning to all of you, my dear students. And today we are going to see some problems in various types of problems in the conductance. Conductance, three types we are going to discuss. One is called the specific conductance, or it is also called, instead of specific conductance, we call it as the conductivity conductance, then equivalent conductance, then molar conductance. And you know the various equations related to each thing. For calculating the specific conductance, the kappa is equal to the conductance of the cell into cell constant. The cell constant is nothing but the distance between the two cells and the area of the one cell, distance between the two electrode and the area of the electrode K. If the L and A are given in terms of centimeter and centimeter square, then the kappa would be having the unit per room per centimeter. On the other hand, if L by A is given in terms of per meter, and here you should write it as per room per meter. During the calculation of the problem, they would give you the cell constant in per centimeter. But you are asked to calculate the kappa in per meter. In such cases, I have given one relationship between the per centimeter and the per meter, but I think I have wrongly given the relation. 10 power minus 2 Simon per centimeter is equal to 1 Simon per meter. All this constant is applicable to per room, and it is equal to 1 or 10 power minus 2 mho per centimeter is equal to 1 mho per meter. This is the relationship. Therefore, you can make use of this relationship, convert to one unit to another. This is for the specific conductance. Then equivalent conductance. The equivalent conductance is given by the equation, and Q is equivalent to kappa, the specific conductance it is necessary, into 1000 by normality. Equivalent conductance, whenever required, your concentration solution should be in normality. If it is given in molarity, you should convert into normality. That is very, very essential. And if you put like this here, the volume is given in milliliter or centimeter cube. Therefore, the equivalent conductance would be having the unit per room centimeter square per equivalent. This is the unit for the lambda equivalent. Sometimes you may be asked in the place of centimeter, what would be the equation for the equivalent conductance in the unit of meter square per equivalent? In such cases, you have to write this equation like this. Equivalency is equal to kappa into 1 by 1000 into normality. Here the volume should be given in meter cube. Here it is given in centimeter cube. Here it is in meter cube. Therefore, you can make use of this equation or this equation, or you can calculate the normality is given and the volume is given in centimeter. You can calculate the equivalent weight, equivalent conductance in terms of per room centimeter square. Then you can convert this into meter square, this unit, by using one relation which I have already given to you, 10 power 4 Simon centimeter square per equivalent is equal to 1 Simon meter square per equivalent. The 10 power 4 may be used in the per or it can be used in before the mo centimeter square per equivalent. Therefore, you can directly find this one, then you can convert this into that one. Or by using the relationship first, you can either go this way or another way. This is the second type problem we are going to work out today. And the third type of problem is the molar conductivity. The molar conductance can be given in terms of the same type of equation as we applied for equivalent conductance, but one difference is that lambda m is equal to kappa into 1000. Instead of normality, you should give the molarity. Here, the volume is given in centimeter cube or milliliter. And then the unit for this lambda m would be equivalent to per rho per centimeter square. What's the difference? Here, per mole would be the final. Here, per equivalent, but here per mole. That's the difference. Therefore, you can also calculate in terms of the meter square per mole. In such cases, the delta M equation would be equal to kappa into 1 by 1000 into molarity if volume is given in meter cube. And here also one unit can be converted into another unit, making use of the same relation as we have given for the equivalent conductance. Therefore, now we are going to see these three types of various types of problem in these three types of formulae. Then we will go for the Gold-Russell law and its application. Then ionic mobility. Okay, with this short introduction, let us start our session. Take down the first problem in this conductance measurement. Take down this one. In a conductivity shell, the distance between the two electrodes, is 2 centimeter, and the area of cross section of electrodes 1 centimeter square. The conductance of the solution is 0.02 per ohm. Its specific conductance in bracket in per ohm per meter. Per ohm per meter is option A 2.1, B 0.04, and C 4.4, D 0.02, which is the correct answer. We will work out with the conventional method. It is given centimeter and centimeter square. Therefore, the cell constant would be in per centimeter, and definitely we will get the unit of this specific conductance or the kappa in per ohm per centimeter. But the answer asked is not the per ohm per centimeter, but it is per meter. Therefore, how to convert into this? For which we will start first calculating kappa. Kappa is equal to C into L by A. It can be easily calculated because there are 4 unknowns are there. The specific conductance, the conductance of the solution, the distance between the two electrode and the area of this one. Anything may be asked giving the other parameters. Here, distance between them is given as 2 centimeter. The conductance is 0.02 and the area of is equal to 1. Therefore, what is the conductance of the solution? 0.04 kappa into what is the unit for this? Per ohm. Here we have calculated in terms of per centimeter. Therefore, this is the. But what is asked? Per ohm per meter. If you don't notice it, you will immediately take this answer. Then this will be erroneous. Therefore, before giving the key answer, see whether the units are same as they asked for us. Therefore, go and this, and how to convert this and that, for which you know the relationship. What is the relationship you are having? Per ohm, 10 power minus 2 per ohm per centimeter is equal to 1 per ohm per meter. Okay, and therefore in this per ohm per centimeter, you should multiply it with this one 0.04, that is equal to 4 into 10 power minus 2 into 10 power minus 2. Now this is equivalent to per ohm per centimeter would be equal to per ohm per meter. Therefore, answer is 4 into 10 power minus 4. That answer, sorry, here the option C, you write it as this one. I have missed the 10 power minus 4. 4 into 10 power minus 4 per ohm per meter. Therefore, now this is the correct answer. Therefore, in both the units, they would give you this value. But this is the correct answer. Okay.
Sir, 4 தான் சார் வரும். 10 to the power minus 4 வராது சார்.
1 minute. என்ன செஞ்சிருக்கோம் நாம? 10 power minus 2 per ohm per centimeter is equivalent to 1 per ohm per meter, and 0.04 per centimeter is equal to 1 into 0.04 by 10 power minus 2. Okay, thank you. Sorry. 4 into 10 power minus 2 by 10 power minus 2. Cancel. Okay. But the given options are correct. Okay. Sorry, but thank you very much for indicating the error. 4 is the correct answer. Thank you very much. And now we will go for another type of problem. The same conductivity, specific conductance. Take down this. A conductivity cell has two parallel electrodes of 1 centimeter apart, with the area of cross section, 0.5 centimeter square, 0.5 centimeter square. The cell constant in per meter is option A 2, B 20, C 200, D 2000. And here a cell constant is simple, but this type of question would not be asked in CSIR because it is below your dignity, and this standard is very, very less. But here it is given, so 1 centimeter apart divided by the area 0.5 centimeter square. If you make use of this, you will be having the unit in per centimeter. But what is asked, you should give the unit in per meter. Here itself, you can easily convert this. Centi, in the place of centi, you put 1 into 10 power minus 2. Centi is equal to minus 2 divided by 0.5 into centimeters. What does it mean? CM square. This means CM power. Oh, this is the correct way of representation. But we are wrongly indicating cm square. If you indicate the meter is in the square form and the c is in the only in the power is 1, don't think like this. Many of the students would be having this type of, and therefore they will wrongly place that value. Therefore, in the air, you should put 10 power minus 2 whole square into meter square. Now you will get the correct answer. What is the answer? Go and complete in your home. Okay, another type of problem. Next, we will have another type of problem. The specific conductance of an electrolyte of point not one normal concentration, not one normal concentration is 0.14 per ohm per meter. Here the specific conductance is given in per meter. The equivalent conductance, its equivalent conductance in bracket in per ohm meter square per equivalent is, close the bracket, is option A 1.4 into 10 power 2, B 1.4 into 10 power 3, C 1.4 into 10 power 4, and D 1.4 into 10 power 5, which is the correct answer. As usual, it is first to write down the problem formula. Specific conductance K kappa is given. Concentration point not one normal is given. Okay, and what is asked? Equivalent conductance is asked. What is the relationship between K, concentration, and the equivalent conductance? You know, K lambda equivalent is equal to kappa into this multiplied by 1000 divided by what should be given here? Point not one normal. Here normality should be given. But be careful. Here the kappa is given in per meter and you are asked to calculate in meter square. But the concentration is given in terms of normality. If it is given in terms of normality and kappa in per meter, here the equation you should use should not be 1000 by 0.01, but it should be, you know, what is the relation? It should be per molarity, per meter square. If you are asked, you should have the formula kappa into 1 by 1000 into 0.01 is not. It is given in, if it is given in this, you will be having this 1 meter square, etc. But sorry, here meter square, sorry, wrongly I have given centimeter square. Here it is given per meter, concentration is given centimeter square. In per ohm centimeter square, per equivalent is asked. Therefore, they are giving in various ways. If you make use of this formula, you would be end up with meter square formula unit. If you make use of this equation, you would end up the answer with per centimeter square unit. But here kappa is given in terms of per meter. Therefore, it is a confusion in this type of conductance measure calculation. Only they would be changing the units. Therefore, you should be very cautious whether go by meter square or centimeter square. We will go by the result. What is the result is asked? Centimeter square. Therefore, we can make use of the equation lambda equivalence equal to kappa into 1000 by the normality. It is, if it is given The unit for this we have already given as 10 centimeters square per equal. Okay, I'm going to take this formula alone. Then if it is there, here n should be in the normality, given in terms of normality. Kappa should be in, the specific conductance should be in per ohm per centimeter, per ohm centimeter. But what is given? 0.14 per ohm per meter, you should convert into centimeter. How to convert this into centimeter? You can easily do this one, 0.2 ohm per ohm. If you do this meter, let us, for the time being, forget the -1. For meter, 1 meter, 1 meter meter, I'm sorry, 1 meter is equal to 10 power 3 centimeter. Sorry, 10 power 10 power 2 centimeter. 1 meter, 100 centimeter is 1 meter. Therefore, 10 power 2 centimeter or the meter. Now put the minus sign, minus power. Now you will be getting the value 10 power 1.4 into 10 power minus 2 per row per centimeter. Thus, you have to convert this per meter into per centimeter. Then now substitute in the equation. 1.4 into 10 power minus 3 into 10 power 3 divided by normality 0.01. This and this cancel. What is the correct answer? 10 power minus 2, 1.4 into 10 power 2. Therefore, the correct answer option is A is the correct option. Therefore, here the conversion factor is very, very essential. And how to convert it is a simple one, but you have to uh, practice the problem, conversion problem at home. Take down the next type of problem. The cell constant of a cell is 0.88 per centimeter. The resistance of the electrolyte taken in the cell is 200 ohm. Resistance is given. The specific conductance of the electrolyte is, specific conductance means they are asking kappa into C into L by A. L by A is given, but conductance we are in need of it, but they gave the resistance. You know, the conductance and resistance are inverse in these to each other. Therefore, you should slightly modify the equation. Now you substitute, you will get the answer. Okay. Next question, you work out in the home. Next question, the equivalent conductance of an aqueous solution. The equivalence conductance of an aqueous solution. 0.01 molar potassium chloride. Equivalent conductance is given, but they are giving it in the molarity. Is 125 per ohm centimeter square per equivalent. The value of equivalent conductance of 0.1 normal KCl at the same temperature is A 125, B 130, C 12.5, D 160. Here no units are given, and in the problem also no units is given, but they have already given the unit equivalent conductance in 125 ohm per ohm centimeter square per equivalent. Therefore, you should take the unit for this is also the same. And how to work out this type of here, molarity. For a univalent electrolyte, you know the molarity and the normality are same. You know the relationship between the molarity and normality. Normality is equal to the molarity divided by valence factor. Yesterday I have given to you valence factor. Valence factor is the number of ions present. Take any one of these, either cation or anion. Number of ions present in the formula, one ion is present. Into what is this valency? 1. Therefore, 1 into 1, this is a molarity conversion to normality. For 1 is to 1 electrolyte, molarity is equal to normality. If it is given as 0.01 mole or calcium chloride, you are asked to calculate the equivalent conductance. Then 0.01 divided by the valency factor. Take any one of the ions, either calcium or the chloride. How many metal ions are there? Cation 1. What would be its valency? Is 2. Therefore, your normality is 0.01 divided by 2. If you take chloride ion, you can take this. How many chloride ions are present in the formula? 2. What is the valency of each ion? 1. Here also you would get the same result. Therefore, either you should take the cation or you should take the anion to convert the molarity to normality. Here we are in need of the normality. Here, this normality KCl equivalent conductance is given. Another concentration they are asking. Therefore, here you have to make use of the equivalent conductance formula twice, and you know the methodology to obtain the unknown parameter. What is the equivalent conductance is equal to the kappa into 1000. Here 1000, then here it is given in centimeters square per equivalent by normality. Okay. If you want to calculate this lambda equivalent, you have to calculate the kappa. Some students may, it is given as 125, therefore this is given, I can calculate kappa, then take the kappa value and I will put in the, once again, this another equation, put the kappa here and the 1000 by the, now the normality is 0.1 normal, then I can calculate this one, but not necessary for this. Substitute, take this equation 2 times. First substitute the first one. 125 is equal to kappa into 1000 by n. What is n? 0.01. This is equation 1. Next, what is asked? This x. This is equal to x. Kappa, the same potassium chloride. Therefore, kappa would be same. The specific conductance would be same. The electrolytes are same. The specific conductance are same. 1000 by what is the normality for which 0.1. This is the equation 2. Now, if you put compare these two equations, put 2 equation 2 divided by 1, you would get the result is x divided by 125 would be equal to this kappa, and that kappa would be cancelled. 1000 by 0.1 into 0.01 by not 1 by 1000. What is the value of Vx? You can arrange this. Therefore, whenever two concentrations are given and you are expected, you can make use of this type of calculation. It would be very, very easier. Therefore, now let us have another type of this equation. Specific conductance, making use of the molarity, and you can do it in your home. Take down the question. The specific conductance of an electrolyte is 0.03 per ohm per centimeter. Per ohm per centimeter. Compute the molar conductance of 1 mole of electrolyte. 1 mole of electrolyte present in 2 liter of the solution. Present in the 2 liter of the solution. Options A, 30 per ohm centimeter square per mole. B, 90, the same unit. C, 60, the same unit. D, 75 per room centimeter square. Here, the answer is given in centimeter square, and for molar equivalent conductivity, we have to measure. Therefore, what is the formula to be used in this type of problem? What is the type of formula? Delta M should be equal to kappa into 1000 by the molarity. That is one. Okay, per mole, therefore we have given the molarity you are need of it and the centimeter square. Therefore, kappa should be in per room per centimeter, whether they have correctly given is or not. Otherwise, you have to convert. If they are giving it in per meter, you have to convert to per centimeter. Therefore, while calculating problems in these conductance, whether all of them would be in the same unit. Okay, it is given in per centimeter, 0.03. Okay, into 1000. Okay, what is the molarity of the solution? And if you see this, 1 mole of the electrolyte is present in 2 liter of the solution. What is molarity? Molarity is the number of moles present in 1 liter of the solution, but in our case it is given as 2 liter of the solution consists of only 1 mole. Therefore, 1 liter of the solution would consist of 0.5 mole. Therefore, here you have to convert that one into 0.5. Don't be very hassle. Therefore, you will end up with the error. Okay, now you know all the things. Then find out the answer. Complete the problem in the home. Next one. Next one. Next problem. The conductivity of a saturated solution. The conductivity of a saturated solution of barium sulfate is 3.06 into 10 power minus 6 per ohm per centimeter. The kappa is given per ohm per centimeter. Per ohm per centimeter. And its equivalent conductance. Is 1.53 per ohm centimeter square per equivalent. 1.53 per ohm centimeter square per equivalent. Calculate the solubility product of barium sulfate. Calculate the solubility product of barium sulfate. Option A, 4 into 10 power minus 6. B, 4 into 10 power minus 3. C, 1 into 10 power minus 6. D, 1 into 10 power minus 9. Here is a two-step problem where you have to calculate the normality of the solution, because you can calculate the normality. Why normality, not the molarity? Equivalent conductance is given. Equivalent conductance is kappa into 1000. Here in the equivalent conductance given in centimeter square, therefore 1000 divided by n. You have been given this value and kappa value. Kappa value is also in per centimeter. It should be per centimeter. Otherwise, you have to change into the per centimeter. Both are given. Therefore, you can calculate the normality of the solution. Normality of barium sulfate solution you have calculated. If you know the molarity of barium sulfate solution, you can calculate the solubility product. The solubility product is barium 2 plus ion and sulfate ion concentration. Therefore, Ksp of the barium sulfate is concentration of barium ion into the concentration of sulfate ion. Therefore, if you know the barium sulfate molarity, since it's a sparingly soluble substance, completely dissociated ions, barium ion, it's a very dilute solution, completely ionized barium ion and sulfate ion. What is the molarity? So many molars of barium ion, so many molars of sulfate ion would be there. Put in this, you will get the solubility product. Therefore, using this data, you can calculate the normality. The next step is conversion of normality to molarity. After converting this normality to molarity, you can go by the another way. Okay. What I have given the last class, normality and molarity, yes, two normal solutions. So, okay. And now we are going to calculate this n. Find out first the n normality of the solution, substitute the values, that is 1.53 is equal to kappa is 3 into not 6 into 10 power minus 6 into 1000 by n, or n is equal to 3 by 1.5 into 10 power minus 6 into 10 power 3 equal to 2 into 10 power minus 3 normality. What would be the molarity? Molarity is equal to normality. What I have given in the last class, last time, molarity and normality relationship. What I have given, a wrong call given, I think so, is not.
Balancing solution.
Molarity divided by valence factor. It's not here I have given like this. Leah?
Yes, sir.
Valence factor, yeah. Here normality is calculated is equal to 2 into 10 power minus 3. And molarity, sorry, ஏதோ wrong-ஆ நான் கொடுத்திருக்கேன்னு நினைக்கிறேன். And normality should be now converted into molarity. You multiply, sorry, okay. You multiply it by 2 normal solution would be equal to 1 molar solution. What I have forgotten, balance factor. Okay, normality.
Sir, normality equal to molarity by 2.
That's normality is equal to molarity by 2. Valence factor is 2. How the valence factor you have calculated? Take any one of the ions. How many ions are present in the given formula into its valency equal to molarity by 2 is the normality. That is equal to 2 into 10 power minus 3. Therefore, now molarity would be equal to 4 into 10 power minus 3. Therefore, what I have, but the answer I have given a wrong calculation. Therefore, 4 into 10 power minus 3 is the molarity of the solution. Okay, the barium sulfate solution is this one. It's a sparingly soluble substance, therefore completely ionized to give barium ion and sulfate ion. Therefore, what would be the concentration of this? 4 into 10 power minus 3 into 4 into 10 power minus 3. Therefore, the solubility product, if you take this one, equal to 16 into 10 power minus 6. That is or 1.6 into 10 power minus 5. simply add the E option 1.6 in 10 power minus 5 and work out this one. That is equal to this is the correct answer. 1.6 into 10 power minus 5. This is another two-step problem.
Sir, last question.
என்னப்பா?
Sir, 4 into 10 power minus 3 கத்து என்ன பண்ணிருக்கோம் சார்?
4 into 10 power minus 3. Either next how to proceed, you don't understand this one. 4 into 10 power minus 3 molar concentration of barium sulfate is present. Since it is a sparingly soluble substance, it's completely ionized to barium ion and sulfate ion. This is a solubility. And what is the concentration of this? Is a completely ionized. Therefore, its concentration is 4 into 10 power minus 3. And its concentration is 4 into 10 power minus 3. Solubility product is equal to the concentration of the ion in power, the number of ions present. Here only one ion is present. Therefore, barium 2 plus ion concentration into sulfate ion 2 minus concentration. Put the values and you find 16 into 10 power minus 6 equal to 1.6 into 10 power minus 5. In the answer, I have not given this answer. Therefore, add this as the E option. Now, 1.6 into 10 power minus 5 is the correct option. Okay, this type of problem may be asked because it is somewhat difficulty level. Therefore, this type of problem will be asked. There is another type of problem. Now I am going to give you, take down this one. Which of the following shells will have higher cell constant? I think so it will not be asked. But however, you should be having experience in this type of problem also. Which of the following shells will have higher shell constant? A. Wire length 100 centimeter and area 100 centimeters square. First, second wire length, that is distance between the two electrodes, is 10 centimeter and the area 10 centimeters square. C option, 1 centimeter cube of a material. The material is 1 centimeter cube. And D, equal in all cases. Equal in all cases. What is this? L by A is asked. Which L by A is higher cell constant? L is length 100, area 100 centimeter, 10 centimeter square, equivalent to 1 per centimeter in the case of first one. The second also 1 per centimeter. In the third, 1 centimeter cube. 1 centimeter cube, is taken to be length is and breadth and the height all are equal to 1 centimeter cube. Therefore, L into B is equal to area is equal to 1 centimeter, height is equal to, or length is equal to 1. Here also, L by A is equal to 1 per centimeter. Therefore, the option is D. Take down the next type of problems, a homework, and I think you will do in your home easily. When a conductance cell is filled with, 0.01 molar potassium chloride, it has a resistance of 160 ohm. It has a resistance. They are not giving the conductance, they are giving the resistance. Therefore, you have to calculate the conductance from this. When the same cell is filled with not 0.005 molar sodium hydroxide. 0.005 molar sodium hydroxide. It has the resistance 190 ohm. ohm. If the specific resistance of potassium chloride is 700 ohm,
Sir,
yeah,
sir, ஒரு டவுட் சார்.
கேள்வி.
சார் ஸ்பேரிங்லி soluble சால்ட்னா கம்ப்ளீட்டா அயனிஸ்ட் ஆகுமா இல்லைன்னா பார்ஷியலி அயனிஸ்ட் ஆகுமா சார்?
ஏதுமா?
பேரியம் சல்ஃபேட் சார்.
Barium sulfate is completely ionized and it is in equilibrium with insoluble solid. When you dissolve this barium sulfate, it would be soluble to a small extent, and it would be those substances which are soluble in that water would be completely ionized. And what is the equilibrium that is obtained? This is the equilibrium you are having in solution. And for the equilibrium constant, we are writing this as barium 2 plus ion concentration into the sulfate ion concentration divided by the activity. Generally, you should, solubility calculation, you should put the activity of the ions by activity of the barium sulfate. You know the activity of the solid substance is 1. Here activity of the barium ion into activity of the sulfate ion. Since the solution concentration is very, very small, in the case of activity, we can make use of the concentration. In the class, you are taught to derive like this. Therefore, now the K, we call it as the solubility product of barium sulfate. Here the activity of the barium sulfate is taken to be unity. Therefore, this and this, you are going to substitute and you will be getting the answer. Now, I think you understand this. It's not undergoing partial ionization, complete ionization. These ions are in equilibrium with the barium sulfate solid, insoluble solid. Okay?
ஓகே சார். தேங்க்யூ சார்.
Okay. Now we are going for the next problem. When a conductance cell is filled with 0.01 molar potassium chloride, it has a resistance of 160 ohm, that is R value is equal to 160 ohm. When the same cell is filled with 0.005 molar potassium chloride, sodium hydroxide, it has a resistance of 190 per ohm. If the specific resistance, here no specific conductance is given, specific resistance of potassium chloride is 700 ohm, what is the specific conductance of sodium hydroxide? They are all confusing. A lot of confusion is here. Don't be confused. I will explain this. What is the relationship between the kappa and this one? Kappa is equal to conductance into L by A. But instead of conductance, they are giving the resistance of the cell. Therefore, kappa is equal to 1 by R into L by A. Now we will substitute this in this equation. The kappa value of the potassium chloride is not given. Instead, they giving us the specific resistance. You know, the specific conductance, inverse of the specific conductance is called the specific resistance is nothing but the kappa. Therefore, 1 by R, 1 by rho is equal to 1 by R into L by A. This is nothing but the rho specific resistance. But here they calculate the specific conductance kappa. They are just confusing you. And now you substitute this parameter here. 1 by 700 is equal to 1 by 160 into L by A. The cell constant is not given. They are measuring the conductivity in the same cell. Therefore, it is not necessary to give you the cell constant. Let us have, this is the equation 1. Now, what is asked here? Calculate the specific conductance of sodium hydroxide. Sodium hydroxide, kappa of sodium hydroxide is asked. That is equal to C by L by A. Okay. And the conductance, whether for the sodium hydroxide conductance is given or resistance is given, resistance is given. Therefore, 1 by 1 R into L by A. What is asked? Specific conductance is asked. X is asked. Now this is equation 2. Now you can divide the equation 2 by 1. You will be having X divided by this 1 by this one. It is becoming 700X. I think you follow this. X divided by 1 by 700 is equal to 1 by 90 into L by A divided by 1 by 600 and this 1 by 160 by L by A. If you all put this, it is equal to 700X is equal to 160 by 190. This and this cancel. And X value would be equal to 160 by 190 divided by 700. This is the answer. You have to calculate what is the correct answer. This type of problem so far not given in the CSR examination, but here all of them are the same, but they are changing the units or the parameters given in various other things. Okay, I think you understand this problem, this type of problem. Shall we go for a next type of problem? Take down this next type of problem. Take down the next type of problem. The specific conductance are the specific conductance are 0.01 normal, 0.01 normal potassium chloride. Potassium chloride is X per ohm per centimeter. Per ohm per centimeter. Having conductance Y per ohm. Having conductance Y per ohm. Find out the specific conductance of 0.01 normal sodium chloride having conductance Z per ohm, having conductance Z per ohm, using the same conductivity shell, using the same conductivity shell. Option XZ by Y, this is the per ohm per centimeter. B, XY by EZ per ohm per centimeter. C, YZ by X per ohm per centimeter. And D, X, Y, I'm sorry, YXYZ per ohm per centimeter. Here you have to take two types of the kappa equation. Kappa is equal to C into L by A. For one potassium chloride apply one time, for sodium chloride apply another time, and put the X for the unknown and find out the value. Is an exercise to you. Okay, the last type of the problem in this one. Take down the problem. the conductance of an electrolyte, or last but one. We can work out a number of problems in this case, but it's a last but one that is sufficient, I think so. Okay, and the last but one. Okay, we will have this one. And the conductance of an electrolyte is 0.224 per ohm. Conductance of an electrolyte is 0.224 per ohm. When the cell constant is 0.5 per centimeter. Full stop. When the cell constant is 1 per centimeter, when the cell constant is 1 per centimeter, L by A value, then option A, kappa increases 2 times, and conductance, that is C, conductance decreases 2 times. B, kappa increases 2 times and conductance increases 2 times. C, kappa remains constant and conductance increases 2 times. D, kappa remains constant and conductance decreases 2 times. Sir, how to answer this? Here you are getting 2 types of cell constant. You are measuring this conductance. This is the conductance. What about the kappa? I have already told you, if you take potassium chloride, the potassium chloride, whatever may be the concentration you are taking, its kappa value would be the same. That is, specific conductance would be there. But the specific conductance between different electrolytes are same. But the same electrolyte, whatever may be the dilution, whatever may be the concentration, the conduct kappa remains the same. If you understand that one, you simply ruled out the first 2 possibility, because the kappa increases for the same potassium chloride, I think so, for the same electrolyte. It is so wrong. It remains constant. Therefore, of these 2 options, one would be the correct option. And you should find out the C, conductance. And you make use of the kappa 2 times C1 L1 by A1. This is the one cell constant. Kappa is the same, C2 L2 by A2. This is another cell constant. Find out C, what is the relationship between C1 and C2, and give the correct answer, whether it increases or decreases. You find the correct way. Okay. Then last type of the problem, the matrix matching type, that is multiple response type. Matrix matching or multiple response. For the same question, 2 or 3 answers may be present, but this type of problem is not in the chemistry, physical sciences questions, but this is frequently appearing for as a section C in mathematics. In mathematics, MSc mathematics students, they are appearing for the CS examination. Section C is a multiple response type. For a same question, 2 or 3 answer would be there. You should write down correctly all the 3 options, then only marks would be avoided. But no negative marking would be there, even if you give the wrong answer. Such type of filling is called the matrix matching type. And I think in future, in CSR also, they would introduce the matrix matching type, break down this list to 1 and list to 2. This type of matching type, it will be very, very simple. If you know one or sometimes one is sufficient, sometimes two matchings, if you are correct, then other matching would be automatically will be setting. First one, conductivity, kappa. 2, molar conductance. Molar conductance, delta M. 3, resistance of the solution. Resistance of the solution. R. 4, degree of ionization. Degree of ionization. This is so far we have not studied. It is given in the Goldross law, ionization of weak electrolyte. Goldross law, one of the application of the Goldross law is to determine the degree of ionization of this one, alpha. Here I will give you the answer. The degree of ionization alpha is given by the equivalent conductivity at a given concentration and the limiting molar conductivity, that is lambda C at a given concentration, and the limiting molar conductivity, lambda naught. Okay, this is the relation. In Kohlrausch law, we are going to give. This is list 1. You should correlate with the items present in the list is 2, lambda C by lambda naught M. To which parameter this one decreases with dilution. F. அடுத்தது என்ன சொன்னோம்? G. Increases with dilution. H. Increase in the distance between parallel plates, that is parallel electrodes. Options, coding means the options 1, 2, 3, 4. A option, F, G, F and H, G and E. For the same, two different answers are there. B, F, G, G, H, and F, E. C option, E, F, F and G, G and E. D option, G, F, F and H, and E, G, E. Here the third and fourth are having two correct answers. This type of is called the multiple response or the matrix matching. Okay, and if you go through this one, here decreases with dilution, increases with the dilution. Looking into this, you can easily come to the conclusion this is related to what? This is related to the degree of ionization. Therefore, for the item 4, the relation is E is the correct one. And what is that? E is the correct one. Here E is given in all this one. Therefore, it is not possible for us to identify this one, whether it is correct or not. Okay. Then we will go for the next It decreases with the dilution of these three parameters. Degree of ionization of the weak electrolyte increases with the dilution. We have already known this one. Degree of ionization. Therefore, for these four, two responses are there, E and G. What are the E and G? This E and G, E and G, E and G. Therefore, B is not the possible one. Okay. Then we will go for the next one. Increases with the dilution. Which is increases with the dilution? Or which is a degree of ionization increases with dilution, we have already seen. Decreases with the dilution, which is undergoing decrement when the dilution increases, which we have already studied while studying the conductivity, equivalent conductivity, that is specific conductivity, and equivalent conductivity, and the molar conductivity. This is a second point or third point I have given. If you go through that, if you find it, the conductivity is going on decreasing as dilution increases, because the number of ions present would be going on decreasing. Therefore, conductivity is going on decreasing. Therefore, for the conductivity, F is the correct answer. Therefore, for the one, F is the correct answer. Here, this is the correct answer because it is E and G, not the right answer. Now we have correlated this one. Therefore, within one or two, I think we will easily match the following. But majority of the students, they won't take this matching because they think they have to match all the four given parameters. Not necessary. If you are lucky enough, if you match any one of these, one parameter, you will be having the correct answer. Okay. That's with that matrix matching. We are, I think, many of the types of problem have been solved. Now we go for the Gold-Ross law and its application. And after seeing the Gold-Ross law, we will have a short look into the ionic mobility and what are the problems that are possible. With that ionic mobility, we will end up the session. And tomorrow's session would be on the transference number determination, then Devey-Hansager limiting law equation and the problem, and finally the conductometry applications. That also tomorrow, Thursday, I'm having the last class in the electrochemistry, and in that way I will finish this one. Now we will take the Gold-Ross law. What is Gold-Ross law? The Gold-Ross law is derived from the limiting DHL I have told you. And what is the Gold-Ross law? It is useful to determine the limiting conductance, whether it is a equivalent conductance or it is a molar conductance. That can be easily calculated. What is Gold-Ross law? What is the statement? It states that at infinite dilution, or at zero concentration, at infinite dilution, where dissociation of all electrolytes or ionization of the all electrolytes is complete. Ionization is complete. And all interionic effects disappears because it's a very dilute condition, and therefore all interionic disturbance or attraction or interionic effects disappears. Therefore, condition is infinite dilution, and where complete ionization takes place and the interionic effects are disappeared, each ion migrates independently Each ion migrates independently. Independent of what? Independent of its co-ion, whatever may be the co-ion. There is no interionic effect between them. For example, if you find out the equivalent conductance of the potassium ion, limiting equivalent conductance, and the co-ion is a chloride ion. At a concentrated solution, the K plus movement is attracted by the Cl minus. I have already told you the movement of the one ion is affected by the nature of the other ions present, the co-ion present. But at very dilute condition, the ions are very, very small. The number of ions are very, very small. And the distance between the ions would be very large. Hence, the interionic effects is completely disappears. And the dilute condition is all the molecules are existing as the ions. Therefore, in that condition, Goldross indicated that condition, any ion will move or will migrate independently of its co-ion and contributes a fixed value of ionic conductance. Look here, a new term is introduced that ionic conductance is represented by the small letter lambda, Greek letter lambda. If you write down the capital letter, it is also lambda, it is a small letter, it is a capital letter. This is meant for the ions present in the molecule. This is meant for either for the cations or for the anions only. This is for this capital lambda is for the electrolytes. Therefore, ionic conductance, I would put within bracket lambda plus or minus. To the total conductivity, the total conductivity they represents, the total conductivity, they call it as the lambda value. The total conductivity of an electrolyte. Once again, repeat the definition. Walras law states that at infinite dilution, where dissociation of the electrolyte is complete and all interionic effects disappears. In that condition, each ion migrates independently of its co-ion and contributes to the total conductivity of the electrolyte. Contributes total conductivity of the electrolyte. And for which we are going to give the what is the relationship between the, under this condition we are going to give what is the relationship between the delta EQ and the lambda of M. The ionic conductance may be given in terms of molar ionic conductance, delta M plus and delta plus equivalent. If you are given these two conditions, one should be converted to another. How is it possible to convert one into another? We will see this, then we will go for the application of this Walras law. The relationship between delta O of the equivalent conductance and delta O of molar conductance. And the first thing I have already given this one, this equivalent conductance is equal to molar conductance by valence factor. The valence factor, how is it possible to calculate this? You are already familiar with this valence factor. And now I am going to give the relationship between the lambda molar, lambda equivalent, that is in the infinite dilution, delta not equivalent, For the cation as well as anion, cation as well as anion, I'm going to this one. Now I am considering a general electrolyte of formula AX and BY, giving X number of A ions whose valency would be Y plus. Sir, how you have find out? Because the Y, if you cross this is the valency of A. If you cross this is the valency of B. Therefore, it is X A valency is Y plus, and how many B molecule ions would be there? B ions would be Y number. What would be its valency? X minus. This is the general ionization character. After ionization, what would be the conductivity of the ions? What would be the conductivity of the ions or equivalent conductance? They may ask you to calculate the equivalent conductance, or you may be asked to calculate what is the molar conductance. Okay, it is possible to calculate this and that. How is it possible? For which you should know what is they would be giving equivalent conductance of the ionic conductance equivalent. They may give and find out the total conductance of the equivalent conductance, or they may be asked to calculate from the equivalent conductance. How would you calculate molar conductance? Or there is another possibility. They may give you the molar ionic conductance. Molar ionic conductance. Using this molar ionic conductance, how would you calculate delta naught M? And are using the molar conductance, you are asked to calculate the equivalent conductance. Therefore, 4 different types of problems they are there, but all of them can be easily solved by which method. I am going to give you the general molar conductance, and you making use of this, you can easily calculate this one. First, we will calculate the lambda of 0 into m molar conductance. Then we are going to calculate delta naught equivalent conductance. If what is asked here, you are asked to calculate this and that by giving 2 types of one. Lambda naught in equivalent, you are asked to calculate this and that, or you are given the ionic conductance in molarity, you are asked to calculate this lambda equivalent and lambda molar concentration. First, we will say you are provided with the ionic conductance of molar ionic conductance. Then we will go for the equivalent conductance. If equivalent conductance is given, how to convert into molar, we will see this. First, we will take one sulfuric acid. Here, the molar ionic conductance are given. Write down how the molar ionic conductance can be made use of to calculate the delta naught of molar conductance of sulfuric acid, for which you should give the ionization of this equation 2H plus plus SO4 2 minus. Here, how many moles of H plus 1 mole of sulfuric acid ionizes 2 moles of H plus ion, and 1 mole of sulfate ion is present. Therefore, here the molar conductivity is given. Therefore, how many moles of H plus ions are there? 2 moles of H plus ion. Therefore, delta H plus naught. It is contributing to the total conductivity. Plus, how many moles of sulfate would be contributing? 1 mole of sulfate would be contributing. Therefore, lambda naught of 1 mole of sulfate, 2 minus. This is equal to, if you sum up 2 moles, 2 equivalent conductance of molar conductance of H plus ion into plus 1 molar conductance of the sulfate ion, it will be equivalent to the total molar conductance of the sulfuric acid molecule. Therefore, if ionic ionic conductance is given molar, and if you are asked to calculate the molar conductance of the electrolyte, it is very, very easier. And now you are going to work out for this one, barium hydroxide. Instead of here you are writing this equation, you can directly write this. How many barium ion is there? Only 1. Therefore, 1 into the limiting an ionic conductance. Which ion you should write down here? Barium ion. Plus, how many OH minus ions would be there? 2 would be there. 2 into the molar conductance. In all the cases, is molar conductance. Here you should write down the molar conductance, 2 OH minus. If you are right, can you write down what would be the molar conductance from the molar conductance of aluminum sulfate from the respective molar ionic conductance? It is given by, that is a lambda naught of molar conductance of the aluminum sulfate is equal to how many aluminum ion would be found? 2 aluminum ion in delta M, that is molar concentration conductance of aluminum 3 plus into the limiting or 0 concentration. How many sulfate ion would be formed? 3 into lambda naught molar conductance of the sulfate ion. This is the one. You will be provided with this value, and with this value you are asked to calculate what is the delta M of the aluminum sulfate. This is the method you have to adopt. It is very easier. If you understand this one, now you are going to write down what is the delta M for potash alum. Anybody? Potash alum. Write down the limiting equivalent molar conductance for potash alum. Write down the formula for potash alum. What is the formula for the potash alum? Write down. Anybody tell me the formula for the potash alum? Or ferric alum? Nobody. Potash alum is nothing but potassium sulfate. You should know what is potash. Alum enna irukano? Your monovalent, univalent salt, sulfate salt, and a trivalent sulfate salt. Trivalent metal ion sulfate salt with 24 water molecule. This should be called as alum. Potash means potassium sulfate, aluminum sulfate. Ferric alum means it is potassium sulfate and ferric sulfate. This is called ferric alum, Fe2SO4 thrice with 24 water molecule. Ferrous ammonium sulfate, you know this, M4, S2O4, ferrous sulfate and ammonium sulfate. Whether you should call it as the alum or not, you should not call it as alum because monovalent sulfate is present. But here it is a ferrous, it's a divalent sulfate and the water molecule is 6. Therefore, you should not call it as the alum, but you should call it as a double salt. Here I am asking for the alum. Here how many potassium ions are there? Therefore, the molar conductivity of this potassium is given by 2 into ionic conductance of potassium ion, 0 concentration, plus 2 into aluminum ionic conductivity, molar ionic conductivity, 0, plus next remaining ion is 4 sulfate ions are there. 4 molar conductivity of the sulfate ion at 0 concentration. This is the relationship between them. You would be provided with the K plus and aluminum and sulfate ion. You are asked to calculate what would be the total molar conductance of the potassium. So is the case with the double salt or triple salt, whatever may be. You can easily calculate based upon this. And the next one is, if at all you are given given the lambda m value, but you are asked to calculate to find out the equivalent conductance for the same substances. How would you find out the equivalent conductance? The equivalent conductance is, you know the formula, the molar conductance divided by the valence factor. Valence factor. And here delta m is given, you should convert the lambda m is given, you should convert into lambda equivalent by dividing it the valence factor for that ion. How is it possible? Yes, it is possible to calculate this. I'm going to tell you, if molar ionic conductance is given, potassium sulfate, sulfuric acid, find out the lambda equivalent, limiting lambda equivalent conductance, for which you have to find out. First, you have to make use of the lambda m of this of H plus. How would you make use of this one? For which you have to find out the valence factor. How many valence factor is there? M is there. You should convert into equivalent. Equivalence. Two ions are present. Okay. And 2 into lambda m H plus. It is already in the case of this and lambda's molar sulfate. You already write down this equation. This is for the molar conductance. Now you have to convert into equivalent conductance. For each ion, molar conductance should be converted into the equivalent by making use of this one. 2 molar conductance. How would you convert molar conductance into equivalent? Divided by its valence factor. Valence factor means how many ions are present, first to find out, and then multiply it the valency of one of the ions. And if you do this, how many ions are present in this 2 H plus, and the valency of one is 1, 2 into 1. And in here, you should divide it by the valence factor. How many ions are present? 1 sulfate ion. Okay. What is this valency? 2. 2 into 1. Therefore, equivalent conductance is given by lambda naught m of H plus. If m of H plus is converted into equivalent conductance by half into lambda of m of sulfate ion. Now note the difference between the delta m and delta EQ. Okay. Note this one. Then how it is possible to calculate the delta EQ? Take anything. First, you find out what is the value for this one. Divided by the valence factor of any one of the ions. Valence factor of, you can take H plus, H2, or you can take the sulfate ion. 1 sulfate and valence is 2. Therefore, divide the delta 0 m by the valence factor 2. If you divide it by 2, you will get lambda m divided by 2, half this one. Therefore, this is the methodology. You can either individually find the equivalent conductance, or you can directly apply this one. Okay, if you understand this one, now you are going to calculate the phosphoric acid, the not equivalence. How to find out this one? அது எப்படி கண்டுபிடிப்பீங்கப்பா சொல்லுங்க. First, write down the delta OM for this. You can easily write it out. 3 into lambda, 3 lambda M of H plus lambda 1 phosphate ion lambda M of PO4 3 minus. Okay, you have to convert this lambda M to lambda equivalent, limiting equivalence. you divide this by valence factor. Valence factor, you can take any one of the ions, either phosphate ion or this one. Here 3 into 1. Or if you take phosphate ion, 1 ion into the charge over is 3, therefore by 3. Therefore divide this by 3, you will get lambda m of H plus. Here all the things you should put is 0 or infinity plus 1 by 3 lambda m of this way. In this way, you can write down this, or individually after writing this is you should be converted into the equivalency, how divided by the valence factor of H plus ion here, and it converting into the valence factor of the phosphate here. You will be having the similar things. Now you are going to write down the equivalent conductivity. How can it be converted to aluminum ion? And the valency factor is 2 aluminum ion, and the valence factor is, சொல்லுங்க, what is the valence factor? Anybody? 2 aluminum ion, 0 Al molar conductivity of aluminum 3 plus divided by its valence factor 2 aluminum, and 1 aluminum is having the valency 3 plus, therefore divided by 6. 2 by 6 is equal to 1 by 3. If you repeatedly do this, you can, looking into this, you can write down the equivalent factors directly. Here 3 sulfate ion would be there, and the valence factor is 6. 3 by 6 equal to 1 by 2 lambda m naught of sulfate. This is the equivalent. This is the, for this aluminum sulfate, we have not write down the molar conductance. Okay, in this way you can write down this. Now you are going to do the problem. Equivalent conductance was the potash alum at home, equivalent conductance. From the molar conductance, ionic conductance. Okay, now I am going to calculate, I'm going to give the methodology to calculate the equivalent conductance and the molar conductance from the equivalent conductance of the ions. Equivalent conductance of the ions. In the case of equivalent, first we will find out the equivalent conductance of the ions. How to find out? For example, H3PO4, let us assume. Wow, how many number of ions may be present here? How many atoms may be present here? Equivalent conductance is given means they have calculated with respect to this. For phosphate ion, they have already converted the molar conductance into the equivalent conductance. Therefore, is just to write down the species alone, not the number, that is equivalent conductance of hydrogen into equivalent conductance of the phosphate. அவ்வளவுதான், முடிஞ்சு போச்சு. This is very easier for this. For aluminum sulfate, if equivalent conductance of aluminum and sulfate ion is there, they have already worked out in converting into equivalent. Therefore, you just add the aluminum ion 3 plus and the equivalent conductance of sulfate ion. Okay, equivalent conductance, no necessity of multiplying this and that. This is just like this. If the equivalent conductance is given and you are asked to calculate the molar conductance, as usual, the equivalent conductance, how to calculate into this delta molar, how to calculate the valence factor போட்டிருப்பீங்களே, that valence factor would be going to the upward, and then you can easily calculate this one. Okay, this is the way you can view the relationship. And after seeing this, we are going to give the applications of the Kohlraasch law. First application, the Kohlraasch law can be used to calculate the limiting conductivity, either equivalent or molar conductivity of a weak electrolyte. Because weak electrolyte, it is not possible to calculate this. For strong electrolyte, we have already seen, we have calculated, and weak electrolyte, it can be theoretically calculated or sparingly soluble salt. Sparingly soluble salt. How is it possible to calculate the sparingly soluble salt, or how to calculate or this one? I am going to give you one problem, then we will see how is it possible to calculate this one. Take down this one at infinite dilution. At infinite dilution. Molar conductance. Oh, I'm sorry. For the first, take down this one. Molar conductance of barium 2 plus ion and Cl minus ions are 187.32 and 74.34 per ohm centimeter square per mole respectively. Calculate the molar and equivalent conductance. Calculate the molar and equivalent conductance of barium chloride at infinite dilution. Barium chloride at infinite dilution. At infinite dilution. Okay, first molar conductance. Which conductance are given? You should make a note of it. It is given as a molar conductance of barium, and these are all lambda m of barium 2 plus, and this is lambda m of Cl minus. Therefore, molar conductance of this barium chloride can be easily calculated. Lambda m at zero concentration is equal to how many ions are there? That ions into the molar concentration of the barium 2 plus at 0 plus how many ions are present? 2 into lambda molar concentration of the chloride ion. Therefore, multiplying point 187 point, சொல்லுங்க 187.32 plus 2 into, for chlorine it is 74.34. You will easily get the molar conductance. Sum these two, you will get the lambda naught m. And you are also asked to calculate the lambda of equivalent conductance. How to calculate the lambda equivalent conductance? From this molar conductance, you can easily calculate this one. What is the valence factor? Valence factor is, so barium, you take any one of the ion, barium, one ion, its valence is 2. Therefore, divide this by 2, you will get half lambda m barium 2 plus. Divide it by 2, you will get lambda m of the chloride. Therefore, if you sum up the lambda m of one chloride ion and the lambda m half of the value, you will get the equivalent conductance value. I think you understand the problem. And now I am going to give the first applications. The weak electrolyte can be calculated, provided if you know the strong electrolyte equivalent conductance. Yes, we are going to calculate this. Take down the problem in this condition. For a strong electrolytes, sodium hydroxide, sodium chloride, and barium chloride, the molar ionic conductance at infinite dilutions are molar, make a note of it, for molar ionic conductance at infinite dilution. 248.1 into 10 power minus 4. For sodium chloride, 126.5 into 10 power minus 4. And barium chloride, 280 into 10 power minus 4. Simon meter square per mole. Make here the color conductance in meter square. Therefore, conductance value is found to be small like this. Calculate delta naught molar conductance of barium hydroxide. Barium hydroxide. How to calculate the delta M of this barium hydroxide, sir? Yes, it is possible to calculate this one. How? First, making use of the strong electrolyte, you should write down the equation so as barium hydroxide should be formed. How it's the sodium barium hydroxide can be formed making use of these three electrolytes: barium chloride treated with sodium hydroxide. Immediately barium hydroxide would be precipitated, and the another is 2 sodium chloride would be formed. We want to calculate this of this one, for which we should know the delta of M of sodium chloride. You should know the delta naught of M of barium chloride and delta naught of M of sodium hydroxide into 2. Okay, if you want to this, you should know this, then you can calculate this one. And you are provided with this data. Therefore, this can be calculated. Take this in the other side, that is minus. Therefore, lambda of M of the barium hydroxide would be equal to, and 0 equal to the lambda naught molar conductance of the barium chloride. Here the stoichiometry is present. How much is present? You should multiply with that stoichiometry. Here 2 sodium hydroxide, therefore 2 into lambda naught M of sodium hydroxide minus stoichiometry is 2 is present, 2 into lambda naught M of sodium chloride. This is the equation you obtain, and substitute the value. You can easily calculate this one. Okay. Sir, this is okay. And how to find out equivalent conductance? If at all asked, here no equivalent conductance is asked. If at all asked, how to find out this one equivalent conductance? Yes, it is easier to find out the equivalent conductance. Sir, how to find out? And for which, for 1:1 stoichiometry electrolyte and the equivalent conductance by this molar conductance is divided by how much? This this is divided by how much? This is divided by how much? For 1:1, the molar and equivalent conductance, if you take only one atom is there and the valence is 1, valence factor is 1, therefore you put it as a 1, and 2 into the molar conductance would be equivalent to equivalent conductance. In this case, the molar conductance is equivalent to this also 1:1 univalent electrolyte. The equivalent conductance and molar conductance are the same. Therefore, put this one, you will get this value. And in here, barium chloride. How much you should divide it? Is something else or not? Yes, you should divide it. How? You should find out the valence factor of any one of the ions present in the molecule, one barium ion, and its valence is 2. Therefore, you should divide it by 2 to conductance of barium hydroxide. Therefore, in this way, you can easily calculate this. If you understand this problem, all other things will be very easier with this. Now you take down another problem in this section, and then we will go for the other types of application. Take down this one. Calculate lambda naught or lambda equivalent naught எழுதிக்கோங்க. Lambda naught equivalent for CX molecule or CX molecule. Given lambda naught for BA, CA, and BX 140, 120, and 198 per room centimeter square per equivalent. They are given all of them as the equivalent they have given. You are asked to calculate lambda naught of equivalent of CX molecule. Therefore, here the CX is formed by making use of this one. For the initial C is present only in this one. Therefore, lambda naught, here all are electrolyte, lambda naught equivalent of Ca should be taken. Then you should add the molecule conductance having X, which is present in the Bx. Therefore, add this lambda naught of equivalent conductance for the Bx. Now you have added these two, and the unwanted is the A and B. That should be subtracted. That is present in the BA. Therefore, lambda naught equivalent of BA. If you subtract this, you will get the CX molecule. Or you can write in this way also. CX should be formed from these reagents. How C is present in the Ca, X is present in the X. When you add this, C and X combines, plus another is the AB or BA. I want to calculate this one, therefore I break this minus AB. Therefore, equivalent conductance of Ca equivalent of Bx minus equivalent conductance of this one. This is what we have written. In this way, you can easily write down this one. And one homework, and you find the answer, and take down the another question. Limiting molar conductivity. Limiting molar conductivity of ammonium hydroxide is equal to ammonium hydroxide is equal to option A, delta M of ammonium chloride plus delta M of sodium chloride minus delta M of ammonium hydroxide. B, delta M of sodium hydroxide plus delta naught M of sodium chloride minus delta naught M of ammonium chloride. C, delta M naught of ammonium hydroxide plus delta M of ammonium chloride minus delta M of HCl D delta M of ammonium chloride plus delta M naught of sodium hydroxide minus delta M naught of sodium chloride, which is the correct limiting molar conductivity of ammonium hydroxide. This is a question asked. Here you can easily calculate this one. Here this ammonium, and it is equivalent to what? If you write this equivalent to what? If you write this, what is equivalent to what? If you write this equivalent to what? We can easily find out that is ammonium ion, this ammonium ion gets cancelled, and here OH minus ion is given, and here chloride ion and sodium chloride minus OH. No product is obtained, is not. Therefore, it is not the correct answer. And if you take down these two sodium ion, one chloride ion gets cancelled, one OH, two sodium and one OH minus ammonium ion. There is no salt formation at all. And here, one Cl and this Cl cancel, two ammonium ion and one OH minus one H plus. Once again, no meaning is there. And if you put it here, one ammonium ion and one chloride ion gets cancelled, one sodium and this sodium gets cancelled. Therefore, remaining is ammonium and OH. Therefore, it is the meaningful is of ammonium hydroxide. In this way, you can easily do this. Or ammonium hydroxide, for which you are in need of what electrolytes we are in need of. I am in need of one compound containing ammonium ion and another compound containing OH minus ion. And what is the cation? What is the anion? Whatever may be this, and this cation and this anion should be subtracted by using the another phase. By that also you can easily find out this one. Then take down the next one. Which of the following expression correctly represent the equivalent conductance at infinite dilution of aluminum sulfate. Given that the lambda of aluminum 3 plus and lambda of sulfate 2 minus are equivalent conductance at infinite dilution. Equivalent conductance at infinite dilution. Option A, 2 into lambda of aluminum 3 plus 3 into lambda naught of sulfate 2 minus. This is the equivalent conductance of aluminum sulfate is asked. Given these are all equivalent conductance. Option A, this one. Option B, lambda of aluminum 3 plus lambda of sulfate 3 plus 2 minus. Option C, lambda of aluminum 3 plus lambda of sulfate 2 minus into 6D 1 by 3 aluminum 3 plus lambda of 1 by 3 aluminum 3 plus 1 by 2 lambda of sulfate 2 minus, which is the correct answer. You go and check. The answer. Okay, this is the first application. And second application, so for 3 applications are there. Now we are going to see the second application. Second application of the Volta's law is to determine the solubility product of Determine the solubility product of a sparingly soluble salt. And we will give you some principle for this. Then only you understand the problem solving section. In the case of sparingly soluble salt, you know only a small amount of the substance is soluble. Small amount of the substance is soluble in water. Hence, the solution of that sparingly soluble salt can be treated as solution at infinite dilution. Only very small would be soluble. Therefore, we can treat it as a solution at infinite dilution. Therefore, the molar equivalent concentration or molar equilibrium concentration calculated by using the experimental data, the kappa, and the values we are using 1000 by molarity or equivalent conductance kappa into 1000 by normality, whatever may be, whether equivalent conductance or molarity you have calculated, we take this value as the value at infinite dilution. We can calculate the value using this equation. But for strong electrolyte, that equivalent conductance at particular concentration, we are writing as lambda C. But for a sparingly soluble salt, it is very, very dilute condition. Therefore, we calculate this as this one. And if you want lambda of naught m, it can be calculated from this lambda value, ionic value, or etc. using Goldras law. And if you know this Goldras law, using that Goldras law, if you calculate the molarity, you can directly apply for the calculation of the solubility product. On the other hand, if you are getting the normality, you should be suitably converted into the molarity. And before seeing one problem, then you should consider another important thing. This kappa, the specific conductance, is additive in nature. The specific conductance is additive in nature. You should keep it in mind, because in some places we are subtracting the specific conductance of water. In some places we won't be subtracting this. For a strong solution, for a strong electrolyte, when you dissolve this, the kappa of the solution is equal to the specific conductance of the salt plus the specific conductance of the solvent. If you dissolve it in water, it is kappa of the water. The salt specific conductance and the water specific conductance, the summation would give you the specific conductance of the solution. Therefore, if you want to calculate what is the kappa value of the salt, you should subtract the specific conductance of the water from the solution. For your information, whenever you use a strong electrolyte, this K solution, that is kappa of the solution, is very, very higher than the kappa of water. Therefore, we can say that the kappa of the salt is equal to kappa of the solution, because its value is negligibly small, it can be neglected. This is for a strong electrolyte. You need not to calculate, subtract the kappa of water, that is specific conductance of the water. Then you apply for the calculation, because more or less the same, no error would be crept in. But for a sparingly soluble salt, the K of the solution, that is the conductivity of the solution, specific conductance of the solution. Here, for this one, if you want to calculate the salt specific conductivity, Now the kappa of the solution is more or less, it is slightly higher than the specific conductivity of the water, slightly higher than the specific conductivity of the water. Therefore, in such cases, for the sparingly soluble calculation, you should subtract the specific conductance of water from the solution. Otherwise, error would be crept in. Okay. In majority of the problem, they would give the specific conductance of the water. Otherwise, you should keep that specific conductivity of the water in mind, and you should subtract the specific conductivity of water is, make a note of it, 4 into 10 power minus 6 per ohm per centimeter. It is also given in per centimeter, not in meter, per centimeter. But majority of the problem, they would give you the value. Otherwise, you keep it in your mind. Okay, and we will now work out a problem or sparingly soluble substance. The molar conductance of barium sulfate at infinite dilution at certain temperature, is 300 per ohm centimeter square per mole. The specific conductance of a saturated solution after correcting, make a note of it, after correcting for the specific conductance of water. They have already corrected it. Therefore, no necessity of you. If specific conductance of water and the specific conductance of the saturated solutions are given separately, you should subtract it. But here they have already corrected for the specific conductance of water is 4 into 10 power minus 6 per ohm per centimeter. That is kappa value of the salt is given per centimeter. Compute the solubility and the solubility product. Compute the solubility and the solubility product. We are going to calculate this. They have given the lambda of the barium sulfate, that is equal to kappa minus, minus or plus, I think, so into 1000. Here it is given in centimeter square, therefore 1000. And per is a molarity, is a conductance is given centimeter square per mole. Therefore, here the concentration should be given in molarity M. Lambda is given 300. Kappa value should be for the barium sulfate is given 4 into 10 power minus 6. Here, if you are given separately for the solution, barium sulfate solution and water, you should give a correction for this into 1000 by M. M is the molarity of the barium sulfate. Okay, the molarity can be easily calculated. Calculate the molarity. What is the molarity of the solution? 4 into 10 power minus 6 into 10 power 3 by 3 into 10 power 2. What is the value? Anybody?
1.3 into 10 to the power minus 5.
1.3 into 10 power minus 5. This is the molarity, that is the solubility. You are asked to calculate the solubility. So many molar solution. Next, what is asked? Find out the solubility product. What is the solubility product? It's a given barium sulfate ion. Therefore, you can directly write the solubility product equation in the concentration of the barium ion into the concentration of the sulfate ion. Being an electrolyte low concentration, the substance barium sulfate is completely ionized. Therefore, you know the concentration of barium ion, and you know the concentration of sulfate ion. Already we have calculated. Now what is the value? Anybody? 1.3 into 10 power minus 5 power and the square. Anybody? .3 into 1.3, how much? It is nearly 1.69 or 1.7 into 10 power minus 10. Okay? This way you can calculate the solubility product. Here, we are calculating the molarity like this. Here, lambda value is given. Sometimes the lambda value would not be given to you. Instead, you would be provided with ionic conductance. Making use of that ionic conductance, you can calculate the lambda value. From that lambda value, then you will be given the kappa value, and the kappa value you can calculate the molarity. Therefore, in this way also you will be given a two-step problem. Now take down the problem as a homework. Take down the problem as a homework. For a saturated solution of silver chloride, the specific conductance is 3.14 into 10 power minus 6 per ohm per centimeter. And that of water used for preparing the solution is 1.6 into 10 power minus 6 per ohm per centimeter. Here water is having this conductivity. Solution is having this conductivity, water is having this conductivity. Therefore, the values are more or nearly same. Therefore, you should make a correction. Otherwise, there will be an error in it. What is the solubility product of silver chloride? Given lambda naught of silver, equivalent conductance of or molar conductance of silver is equal to 68.3, and that of chloride is 70. That of chloride is 70 per ohm per centimeter square. Centimeter square per equivalent. And making use of this, you can calculate the lambda of the silver chloride. Okay, that can be easily obtained. Here, equivalent weight they are giving. Here, 1:1 electrolyte, valence factor is 1. Therefore, equivalent weight or molarity are one and the same. Silver chloride is equal to kappa. Kappa value is, the solution is given and water is given. Therefore, you subtract and find out the kappa. And it is in per centimeter. Therefore, you put it in 1000 and the molarity. Now, you calculate this lambda, this from this, and you calculate from these two and find out the molarity. And after seeing the molarity, apply silver chloride. Therefore, solubility product would be KSP would be directly concentration of Ag plus and into the concentration of Cl minus. Apply this and you will find out the answer. Okay, if for aluminium, for example, aluminium hydroxide or say ferrous phosphate is given. What would be the solubility product? Equant, right, is directly KSP would be how many ferrous ion would be there? 3 ferrous ion. Therefore, concentration of ferrous ion power 3 into the concentration of phosphate ion power 2. Therefore, you should be accordingly calculate the solubility product. Okay. And think you complete this problem and work out it, you will be well acquainted with the second thing one. And two more type of problems so far not asked, but maybe somewhat difficulty problem. Tomorrow we will see this. And the third application, the degree of ionization calculation, alpha is equal to lambda by lambda not, lambda in one concentration and lambda at infinity. Making use of this, what are the possible problem that can be asked? Tomorrow we will see that. That is one type of the problem. Then we go for the ionic mobility, then limiting law method, and then finally the conductometry. Tomorrow, not tomorrow, the next class on Thursday. On the Thursday, I will finish this electrochemistry, however. And until then, you search for the one thing. Here, the solubility product. This one concentration into another concentration. Here, the solubility product. 3 concentration of iron 2 plus and 2 concentration of phosphate. Therefore, 5 concentration terms are there. Whether the solubility product is having any unity or any unit or not. Tell me, find out and tell me that whether it is having any unit. Do you give any unit for the solubility product? Or do you think there should be some unit for the solubility product? தேடுங்கள் கிடைக்கப்படும். Okay, is there any doubt? Shall we wind up this session?